So the diffusion method that we've seen so far, when applied to images, was done in pixel space. So the noise had the same resolution as the image, and the denoising U-net had to operate at pixel resolution. And for several reasons, this turns out to not be the best choice. So one problem is that diffusion in pixel space is computationally expensive and therefore slow. So dealing with essentially these large tensors passing through the U-net becomes a lot of computation, and that's slow and expensive. But data such as images, and this would apply to many other modalities as well, is very compressible. We know that because we use image formats like JPEG, which are able to dramatically reduce the file size, but perceptually, when it's uncompressed, the image looks very similar to the uncompressed one. So I'm going to introduce a concept called latent diffusion, where the idea is to pre-train a variational autoencoder to encode images, or it could be other data, to a latent space and decode back to data space. And then what we will do is train the diffusion model to operate on encoded images, so in this reduced dimensionality latent space. So with such a model, if we want to generate a new random sample, then we actually generate our noise in the latent space. From there, we can denoise with the diffusion model that operates only in this latent space, and then we decode back to the data space. So actually, for generation, we'll never use the VAE encoder. So roughly what this looks like is you would take your full resolution image, pass it through your VAE encoder. Of course, because it's a variational encoder, you would then do some sampling to get the actual latents. You're then in this low dimensional latent space where you can add noise or generate noise and put it through the denoising U-net. And then you can decode from this latent space back to pixel space without really losing much quality at all. So to give you some concrete examples, in stable diffusion that I'll talk about in a moment, the VAE is trained on 512 by 512 images, and the latent space is 64 by 64 with 4 channels. So there's a 48 times reduction in the size of the data with very little loss in quality. So it's quite important that this VAE is trained in order to do perceptual image compression. What that means is we want the VAE to provide a latent space which is lower dimensional, so we can see we've got that from the slide before, it's 48 times smaller, but we want it to be perceptually equivalent to the data space, so no loss of quality. And to achieve that, the reconstruction error that is used in training the VAE is crucial. So we don't just use mean squared error. It combines two things. One is a perceptual loss. So this is a reconstruction error that better correlates with human perceptions of differences between images. And then we also have a patch-based adversarial loss like in a GAN. So this is to try to make sure that the sort of high frequency detail that you see in regions of an image are well reconstructed. So knowing this overall process, we can dive in and look at a modern, very successful architecture for image diffusion, and that's the stable diffusion method. So we can see our original data here, X, passing through the encoder to enter the latent space. And the diffusion process, so this is the forward diffusion process, is the process of adding noise, which is now done not to the image, but to these latents instead. This gives us our ZT. The ZT is then denoised. It's the same as before. We have a denoising U-net, and the job of the denoising U-net is for each pass through, we need to predict the noise, the epsilon, that we think transformed the slightly less noisy Z at t minus 1 into ZT. So we do that multiple times for t going from time going from t all the way back down to 0, where we have a fully denoised latent, and then we can decode that back to pixel space and get our image. Of course, if we're just generating, we wouldn't do this encoding and forward process. We would just start with a random ZT here. Now, there's one extra detail that I'm going to talk about in a moment, which is that this generation process can be conditioned. And what that means is you can provide something like a text prompt or an image or maybe a map laying out the semantic components you want in your image. That's passed through another sort of embedding network, tau, to provide a sort of conditioning label which should influence the output of this. So, for example, if the text prompt describes some particular type of image, we want that to influence the generation, so the image that comes out the end is consistent with that text prompt. And the switch here is just showing that two variants of stable diffusion were considered. So in one version, this embedding of whatever your conditioning information is was just concatenated onto the noisy latents and passed into the denoising U-net. Another version uses attention. So in that case, the conditioning information is used as part of the attention mechanism throughout this denoising U-net, and that's actually a more powerful mechanism. So let's see, how can this conditional generation actually work? How could the denoising U-net somehow be able to ingest conditioning information and actually reflect that in the output? So what we want is semantic or intuitive control of the generation. So specifically, if we're given some label y, what we want to be able to do is sample from p of x given y. So this is now the distribution of possible images x that are consistent with the label we've been given y. Now, we already have a way of building a good model of the data space, so the distribution of our images or our training data, p of x. So we've seen that if we train a pixel denoising diffusion model, or we could do the same thing in latent space, we get a really good model where we can randomly sample noise and then denoise that back to a very plausible sample of the distribution of images. Let's assume that we also have some good discriminative model. So we can then say, what's the probability of a given label y given that we've observed x? So this is exactly like the sorts of discriminative models we've been building. So whether it's classifying MNIST digits or something like that, that's exactly what this discriminative model would do. Now here's the nice trick. By Bayes' rule, we can use this, so our model of the distribution of the data and our model of the distribution of the label given the data, we can combine them to compute the distribution of the data given the label. So, for example, this conditional distribution might be an image classifier, like I said, so it might be something that classifies what digit is in an MNIST image, or it could be a classifier for the content of an image, for example. Then we've got our image generator, which can be a diffusion model, and that allows us to essentially create a class conditional image generator. So we get a class to image model for free. We don't need to retrain the diffusion model. We can do that just by having access to this discriminative model, this classifier. So how do we actually do this? So during denoising, we calculate the gradient of the classification loss with the given label with respect to the current denoised image, so our xt. So we're basically saying, let's say the label that's been assigned to xt is cat. It's supposed to be an image of a cat. We can put the current noisy image into the classifier with the label cat, and we can compute a cross-entropy loss. And if we calculate the gradient of that with respect to the image, it tells us how would we need to change the image in order to make this more like a cat, assign higher probability to a cat. So we can add that, the gradient of this classification loss, to the predicted noise and use the two things together as an update. So basically, when we make one of our diffusion steps, we're slightly denoising the image, and we're also slightly making it more like a cat, if that's the target label. And this classifier gradient is weighted by a parameter called the guidance scale. And what the guidance scale does is it basically trades off diversity and realism. So when the classifier guidance weight is low, we get realistic images, and we'll see a lot of variability as we change our noise. When the classifier weight is very high, the variability is much less, and the quality starts to suffer. So you can see the colors have become a bit saturated, it's lost some detail. Now, that's okay, and it works. However, it is a bit limited. What if we wanted to condition on something other than classes? Or what if we wanted to generate a class that we didn't have access to at training time, so when we trained our classifier? Or what if you just don't have a suitable classifier? One of the drawbacks of classifier guidance is you need a classifier. So either you have to train it in advance or alongside this process. So something called classifier-free guidance makes it possible to achieve the same thing but without a classifier. In fact, it turns out to work even better, and it's a really clever little trick. So the downside, which I'll mention straight away, is that you do have to retrain your diffusion model. So the diffusion model must be trained with this conditioning, whereas that wasn't true for classifier guidance. So what we do is we make the backward diffusion model, the thing that predicts the noise, conditional on some label, or in fact it can be anything, some embedding of something, y. So it doesn't need to be like one of a set of possible classes. It could, for example, be an embedding of a text sentence by any appropriate network. So we can see now our network that predicts the noise that's been added in the last diffusion step now depends on the current noised element, the time, but also this label or embedding, this conditioning information. What we do is at training time, we just randomly choose between giving the denoising diffusion model the label, or giving it a sort of null label. So in practice, this would probably be all zeros. And the idea is that the denoising model, if there's useful information in the conditioning that helps it generate this image, then it will learn to exploit that, even though we're not explicitly guiding the output image to do that. And then what we can do is at inference time, when we want to generate an image, we can denoise both with our target label, so the thing that we want it to preserve, and without, and look at the difference between them. And this difference should push the result in the direction of generating something more like this target. And again, we have a parameter that controls how much we focus on this conditioning information. So the change to the update at each step is actually quite small, but the effect is remarkable. So now anything that we can embed into some conditioning information, y, we can now use to control the generation. And this is how the amazing text to image models work. And I'll show you a few other examples here as well. So This is a text to image model, and you can see the richness of the variation. So we've kept the prompt the same and used 4 different random latents to initialize. The first 4 look kind of like photos. The second 4, it says an oil painting, and you can see it's kind of captured that style. It's kind of interesting to look when it's asked for a street sign that reads latent diffusion. It actually struggles with text. This is probably just the wrong representation to learn how to create text. The example at the top is conditioned on completely different information. These are now bounding boxes in the image along with a label. So basically in the top row I'm saying I want a train in this region of the image and I want some trees in this region. If I have some means to embed that into the latent representation Y, and I suitably train my diffusion model to have access to this layout information at training time, then it can learn to do that. So here's 4 different generations from this conditioning information, and you can see they're all consistent with the desired layout. In the bottom example, we've specified a vase and some flowers, and again, all of the generations are consistent with that.